So for this video, I'm going to be talking about the concept of chi-square or chi-squared. This is written like this: chi, the Greek letter chi, square, it's a squared value. And really what this value is it's a representative of how good a fit is if you try to fit data. This is actually what the computer is doing when you do a fit to data. It's actually calculating this value, or it's trying to minimize this value. But it also can be used to tell you how good the fit is if you actually calculate it. So in order to understand it, let's draw some data. So I have some data here, and I have a couple of data, and they each have their own error bars because we did a good job finding error bars. Of course, there's x data, and there's y, there's x value and a y value. And you're trying to find... All right, so you have some data, and you say, okay, this data looks like it might be fit to a line, so I'll fit a line to it. Let's say the fit comes out something like that. So then you might ask, how did the computer actually do this? So what the computer is actually doing in this case is it's looking at the difference between the data point here and the fit itself. So this value here, basically, the difference between the data and the fit line. And it's trying to, and what it does is it adds those up for all the different data points, and it tries to minimize that value, basically trying to say, I'm going to put the line right in between it. And so this will be helpful if we actually have the equation for chi-squared here. So chi-squared is equal to, you sum over all of the data points, so I equals 1 to n. And then you have on the numerator here, you have the individual value for the individual data point minus the fit value, the value that you're going to be finding when you fit it at that position. And then you square the value, just like standard deviation, you square it because you're going to get just as many points above the line as below the line. So you want to get rid of the fact that some are positive and some are negative. And then you divide this by the uncertainty on each one of those data points. Actually, this, apologies, the square is for the whole thing. You could have just put the square in the bottom. It doesn't really matter too much. Yeah, so what your computer is actually doing is it's going through when it tries to fit a function, and it calculates this value, and then it runs it again, and it changes the line a little bit, and it says, how does this chi-squared change? Does it get bigger or smaller? If it gets smaller, it continues along that way, and it does this until it kind of stops. So for some fitting algorithms, you can tell it how many iterations to go through. MATLAB is actually really powerful for this. Has a little bit more control. Again, I'll suggest Python in this course. It's a little bit simpler to calculate these kind of things. But it'll actually go through and do this. For a line, there's actually an analytical solution. You can do it by hand. The equations are actually in that data handout if you wanted to use those. I wouldn't suggest doing that by hand. Anything else, power law, exponential, if you're fitting a sine or a cosine, like anything else, there's not an easy analytic solution, so you have a computer finding a local minima and trying to minimize chi-squared. So this is what your computer is doing, is it's trying to minimize this function. It's really trying to minimize the difference between the individual data points and then the fit at that position, right? So it's trying to minimize that. And that's why the line goes in between them, because some of these lines will have a difference, the data point between the line right there, and some of it's negative, and it kind of puts it in between. So then you might ask, okay, so if that's true, how are we going to actually use that in this course? Well, the other thing is that if you did a good job fitting this, what you would find is if this is a good fit, what you would find is that on average, the individual value minus the fit value squared is going to be approximately, at each individual position, the uncertainty. And so the idea there was that your fitting line would pass through all the error bars. So like this example I have here, you can see the fitting line passes through that error bar. This one it just missed. This one's on the edge. These two it passes through. So it kind of does that. So on average, the difference between your data and the fit, if that is inside the uncertainty for the individual data for all the data points, then you have a good fit. And so that's what it would look like. So if it's a good fit, if that's true, that means that chi-square or chi-squared, if you add up all the points, would be equal to n. So for a good fit, you have chi-squared equal to the number of fitting data points that you have, and that's what you would get. This is not exactly true. I'm kind of hand-waving some of this because what does matter is how many fitting parameters you put in here. For example, if you fit This looks like a simple linear line, y equals ax plus b. You could try to fit y equals, you could fit a quadratic, ax squared plus bx plus c, and it would fit it as well, and it might fit it almost as good. But so you have to take into account the fact that if you add more fitting parameters, you're going to get a better fit. That doesn't mean it's more representative of the data. So really, what we do is we calculate something called reduced chi-squared. Reduced chi-squared has a little bar here. Or chi-square reduce. You could also use that as well. Maybe that's what I'll use for this today, just so that doesn't look like an average. Reduced chi-square is actually going to equal to chi-square divided by n minus, what variable should I use here? R. And R here, let me make sure I'm not overlapping with my video. No, we're good. R is the number of fitting parameters. So this would be, if you fit a line ax plus b, it would be 2 because a and b. So in this case, that's what reduced chi-squared is. So if a good fit, reduced chi-squared should be approximately 1. And so this is what you're going to actually do in this class whenever you do a fit. I have a new Python code that actually calculates this for you. It's quite easy to calculate. You can see the equation right here on the left. You just have to do calculate the value minus the fit, calculated fitting value at any position, square that divided by the uncertainty in the individual. So you actually need y uncertainties for this, which is really important. We haven't talked about x uncertainty in this class. It's really easy to plot Python with x uncertainty. See if you can figure it out yourself. You can look at the code and kind of figure out where to add in a line to put x uncertainties. And you should do this if you have x uncertainty. Adding x uncertainty into chi-squared calculations is a little harder, so we're not going to talk about that. But you can see the reduced chi-squared, you're going to want to get close to 1. You might be like, what's close to? This is all based on probabilities. There's actually really big charts. There's one at the end of the day to hand out. What these actually mean. If I got a chi-squared of 1.2 or reduced chi-squared of 1.2, what does that mean? There's things you can, there's values you can talk about there. I think I'm going to leave that for a statistics course. It gets really gnarly pretty quickly. But this is just kind of see. So if you, for example, this is actually most useful if you have 2 fits. Let's say if you're not sure if a fit should be a linear ax plus b or just ax, what you could actually do is do both fits, calculate reduced chi-squareds for both, and the one that has a smaller reduced chi-squared is the better fit. So it's actually the most useful if you're comparing 2 different fits. Let's talk about the actual value itself. It should be close to 1. If you get a reduced chi-squared of 1,000,000, that means your fit's bad. If you look at the equation to the left here, that would mean that your data points minus the fitting line, the difference is really large, right? But there's actually a second thing it can tell you. If you have a really large chi-square, the numerator could be big here on the left, but also the denominator could be really small. So if your error bars are too small, that would also yield a chi-square that's too big. So the chi-square can tell you a couple different things. It's not a simple, I got the right answer, I got the wrong answer. Everything in kind of real data manipulation, plotting, and doing experiments is not so clean cut. So you just want to take a look at it. So if it looks like your line fits your data, but the error bars are really small, that would yield a really big chi-squared, even if the fit's good. On the other hand, if your chi-squared is really small, instead of getting a reduced chi-squared of 1, you get like 0.01. That tells you there's something weird going on. And what likely is happening is that your uncertainties in that case are too big. It's telling you, like, I think your uncertainties are incorrect. So maybe I'll put that up here on the top right here. So a high chi-squared, let's say reduced. This can be either from bad fitting, right? So this means that the numerator is large, or small error bars. Their error is too small. A too low reduced chi-squared, again, much smaller than 1, this can be mostly probably due to error bars that are too big. There's actually something else that can happen here, or fake data. So if you falsify data, it's really easy to fake data, make it like, oh, look, it looks like a line. If you fake it poorly, the reduced chi-squared will be way too small, and it actually tells you that data is fake. So people have been caught doing that. So that's basically the idea for chi-squared. It's kind of a simple concept. You're just you're minimizing the difference between data and fits at any point. I've given you the Python code to calculate this. So going forward, any fits, I want you to calculate it. Especially in this class, mostly we're doing linear fits. If you're not using Python, you really want to use MATLAB. Just calculate it yourself. Just look at the code, or just write your own function or own code line using the equation to the left. It's quite simple to do that. Okay, great, and I will see you guys later.